Welcome to this lesson on indicators and the pH scale. To get started, we're going to look at a quick little intro video.
That's the best you can do? Watch this. Get on the floor and let's shake some asses. We're fiery and hot, not calm and placid. We burn through material and make it quick. We even digest the food in your acidic stomach. It is I, the pH scale. If I were to rate your singing on a scale of 0 to 14, acids would be below 7 and bases would be above 7. And you are about to find out why.
Alright, so to start off with, we're going to look at this concept of an indicator and what it actually means to be an indicator. So traffic lights are indicators. We've seen them all the time. What do? They tell us whether we can stop or whether we can go. They tell us what actions that we can take in a scenario. The color of the light, the indicator, tells us what to do, whether we can go on green, stop on red. So an indicator in science is virtually the same thing. A pH indicator, and we'll talk about what pH means in a little bit more detail soon, are substances which are normally a very weak acid or base that actually changes color depending on what it's mixed with. So whether you mix it with an acid or a base, it changes its color to be a different color. We use this indicator to find out if a substance is an acid or a base. So it's the easiest way to do it. There are perhaps much more complex chemistry ways you can do it, but you can do it very, very simply. And we'll actually do an experiment with red cabbage. So you can just dissolve red cabbage in water, creates a purple liquid, basically just like purple water, cabbage water. And if you add acids and bases to it, the mixture will change color. So you can create your own indicator using things you've got in the kitchen. So the pH scale is a table or a scale from 0 to 14. And anything from 0 to 6 we say is acidic. And from 8 to 14 we say is alkaline or basic. So alkaline and bases are sort of the same thing. Alkaline is sort of the proper term, but often we just call them basic. And 7, smack bang in the middle, is neutral. So something with a pH of 7 is neither acidic nor basic. So if we mix the in this case, the red cabbage indicator that we've made, and this is what we're going to do in an experiment, we're going to see different things. So if we go more towards the alkaline scale, we're going to see the purple sort of color starts to change pink. In more of an acidic case, we might see that it actually changes to more of a purpley sort of color. So we're going to actually test that in a lab. But that's what we're looking for. We look at the color change, and then we match it to a chart to try and see what kind of acid or base we've got. So there's actually lots of different types of indicators. If we want to be really certain, we don't generally just rely on cabbage. We're going to use a few different indicators. Most indicators only have 2 colors. So sometimes we need to use another indicator to sort of refine it or just confirm what we've got. In this case, you can see on the right hand side, these are a few different indicators. So we've got the pH scale across the top, 0 to 14, bases and acids. And you can see in this case, we've got a universal indicator. We've got this thing called phenolphthalein. We've got methyl orange, thermal blue, bromethyl blue, and phenol red. And you can see that they all create different colors. So you'd have to basically calibrate these indicators to a chart so that if you know the indicator you're using, you check the chart and you match the colors to that. So if we get pink from a phenolphthalein, then we expect it to be basic. If it's basically nothing, well, that's useless. So phenolphthalein is only good for basics. It can't tell us about acids. Whereas the methyl orange would give us basically nothing if we use it for bases, so it's useless. But if we get really strong acids, it will start to change. So again, great for really strong acids, not great for weak acids, and definitely useless for bases. So here's an example of what the chart may look like. It's not exact, and this is part of the challenge, is if you had a color that you're like, right here, it's very difficult to identify, is it sort of a 7 or an 8? Pretty much across this, it's impossible. This is why the litmus is not ideal, because it'll tell you, yes, it's basic, but we don't know how basic. We also don't know how acidic. We just know it is acidic, but it could be acidic of 6, could be acidic of 0. And that's pretty important. Universal indicator is actually a combination of lots of different indicators. So we often use this a lot because it's pretty good. And if you remember back from the previous slide, the universal indicator here really gave us the greatest spread of colors. So we use that often because the different colors can be mixed and it gives us a much more accurate reading on both whether it's acid or base, but also how acidic or how basic. So let's look at the pH scale. The letters pH stands for potential of hydrogen. It's really just a chemistry term. It's a measure of the concentration of hydrogen ions in a substance. Doesn't really mean a lot to us, doesn't really need to. It's just what it means. We just call it the pH scale. So it's a scale from 1 to 14, tells us how acidic or how basic a substance is. As I said before, less than 7 is acidic, greater than 7 is basic or alkaline. So if I'm adding an alkali to an acidic solution, so what we're saying is you've got a solution of acid and you add an alkali to it, the pH level is going to increase because acidic solution is low. Remember, it's less than 7. And I'm adding an alkali, which is greater than 7. So it's going to slowly increase the pH. It's actually going to make it less acidic, which is increasing the pH. So if you can get your head around that, like as I'm making it less acidic, it's actually increasing the pH. It's getting closer to 7. And that's what's going to happen. However, if I add an acid to an alkaline solution, then the pH is going to decrease because it starts off really basic, so greater than 7. I'm adding an acid which is going to pull it down closer to the neutral, so it's going to decrease. In life, the pH of liquids in your body varies from organs, from one organ to another. In your stomach, for example, the acidic conditions pH of 1.5 are what your stomach acid uses for digestion of proteins. It's really, really important. But that's really, really acidic. If you get acidic pH of 1.5 on your skin, it's going to burn. So your stomach lining, the mucus in your stomach lining is specifically designed to protect your organs from the rest of your, or the rest of your body from the acid inside your stomach. In your small intestine, for example, the alkaline conditions are about a pH 8, so they're slightly basic. And again, that's needed to digest the food that travels through your small intestine.
From the tangy bite of a piece of fruit to the caustic liquids used to clear a clogged sink, acids are a type of chemical that could be found in many different aspects of our daily lives. But what is it about acids that makes some safe to eat and others dangerous? When talking acids, we're going to be talking hydrogen. Not the gas, but rather the hydrogen ion H+. This is a hydrogen atom that has lost its one and only electron. All acids produce H+ ions when dissolved in water, but it's how much H+ a specific acid can produce in water that will determine whether it can be safely eaten or not. But how do we conceptualize and measure H+ concentration? Søren Sørensen, a Danish chemist, pondered this question when he worked at the laboratories of a commercial brewery in Copenhagen. It was in 1909 that he developed a method of quantifying acidity, what is now known as the pH scale. His scale works by simply converting the concentration of hydrogen ions in a solution to a number between 0 and 14. If a chemical is acidic, then its pH will always be below a 7 on the scale. The lower the number, the higher the hydrogen ion concentration. The pH scale is a logarithmic one, meaning that 1 unit difference on the scale, say from 3 to 2, means a 10-fold difference in H+ concentration. But 0 to 7 is only half of the picture. So what about all these numbers above 7? Substances that correspond with this half of the scale are called bases, and they are the chemical opposites of acids. The 7 on the scale represents neutral pH, what would be perfectly pure water. Like acids, bases are found in chemicals that we encounter in our everyday lives. Cleaning products such as ammonia and baking soda are bases, as are some simple medicines like milk of magnesia. They're bitter to the taste and often slippery to the touch, kind of like soap. Even though bases are different than acids, they too can be strong or weak, and a strong base can be just as dangerous and corrosive as a strong acid. Chemically, the difference between acids and bases is that acids produce hydrogen ions and bases accept them. In water, acids produce H+ ions and bases produce OH- ions. In reactions between acids and bases, hydrogen ions will react with hydroxide ions to make water. This type of chemical reaction is called a neutralization reaction. Acids and bases are also very important in biochemistry. Many biological processes are sensitive to the pH of the surroundings, so controlling acidity in the body is crucial. Some biologically important molecules like amino acids have dual personalities. They're said to be amphoteric, which means that they can act as both acids and bases. An amino acid has a carboxylic acid group that can produce hydrogen ions and an amino group that can accept hydrogen ions. Acids and bases are all around us and can vary greatly in terms of their use and their nature, but they all involve hydrogen ions being passed around. Thanks for watching.
Alright, so that concludes the lesson on acids, bases, and the pH scale. There will be a quiz associated with this, and I will see you next lesson.